We have another example here. We have a box. We're applying this external force P shown in the picture. It's at an angle of 30 degrees with the horizontal. Let's see, we push a distance of 8 meters, so this is our delta S. Our speed changes from an initial speed of 0.5 meters per second to a V final of 2.6 meters per second. And we want to find the work done by friction. So to relate forces to speeds, that is our work-kinetic energy theorem. The net work done on this box will equal the change in kinetic energy of the box. I'm going to go ahead and jump to the point where the final kinetic energy is 1/2 mv final squared minus the kinetic energy initial, so 1/2 mv initial squared. Okay, so the net work, we need to consider all of these forces. So if I draw my free body diagram over here, I like to draw my forces emanating from my dot. So there's a force P at this angle 30. There is a normal force. There is the force of gravity. There is some friction. And I certainly did not draw these to scale. When we say net work, we mean the work done by every single one of these forces while the object moves, while this box specifically. But we know this box is moving horizontally to the right. So all of these forces are constant. When the forces are constant, we can say the work is the force dotted with the displacement, delta S, or F delta S cosine theta. So dot product, it's only accounting for the force that's parallel to the motion. That cosine theta is accounting for that generically, but ultimately in this specific problem, the work done by the normal force will be 0. The work done by the force of gravity will be 0 because those are perpendicular to the direction of motion. So we're going to have the work done by force P, this push, and the work done by friction. So coming over to our work-kinetic energy theorem, we can say that the work done by the push, that external force, plus the work done by friction, that represents the net overall work done, that will equal the 1/2 mv final squared minus 1/2 mv initial squared. Now this particular problem is asking us for the work done by friction, so we're only wanting to find this term, the work of friction. Okay, so work done by friction, we need to figure out the work done by the force P as well. Since the pushing force is constant, it tells us that in the problem, we know the value of the force, we know the angle it is acting at from the picture. I'm going to just write this over to the side. The work done by the pushing force, well, it's only the component of this pushing force, the x component, that is in the same direction as the displacement. We want the x component of the pushing force times our delta S. But thinking back to our vectors, that x component of the push would be P cosine 30. So there's our force times delta S. which, by the way, if we use this equation, P delta S cosine, the angle between those two vectors is 30. So we get there the same way. I find it helpful to make sure you're reasoning through those parallel components. So that's why I showed that at this point as well. So this term is what's going to go in over here on the left for the work done by the push. I'm going to bring it to the other side, though. I'm going to go ahead, just for plugging in sake. I'm going to factor out the 1/2 m, and then we'll have v final squared minus v initial squared, which, by the way, is not the same thing as v final minus v initial squared. Don't do that. I need to bring the work done by force P to the other side, so I will subtract it. Oops, 30. And unplug in this work that we know is done by the force P. So the work done by friction. Plugging in values, the mass of this box is 20 kilograms. V final, the final speed is 2.6. The initial speed was 0.5. The pushing force is 160 newtons. It acts over 8 meters. And that cosine 30 term is accounting and for only the parallel component. I'm getting negative 1043 joules. Let's see, we have 3 sig figs, 1.04 kilojoules. The negative sign, we should have expected that, because friction's working, trying to slow the box down, not allow it to speed up. So friction is taking work out of the system. We say that friction is creating and turning some of the system's energy into thermal energy. We could say there is 1.04 kilojoules of thermal energy created or transformed. So I guess the best way to say it, 1.04 kilojoules of kinetic energy transformed to thermal energy of the system. Thermal energy is always the energy related to the temperature. As two surfaces slide together, they become warmer. The temperature increases, and that's why this is considered thermal energy, which we will refer to that more so as we continue on, especially into the next chapter.